Okay, so exam review. So obviously, we just finished learning all the material that we're going to learn in this class. So let's go through and do a really quick overview of all things that you can expect to see on your exam. The first thing that you should expect to see is prime and composite numbers. So for this, you'll want to know things like the sieve of Eratosthenes and how to find runs of composite numbers. So multiple numbers in a row that aren't prime. You'll need to know how to do count divisors and relative primes. So using the prime factorization to compute those kinds of things. You'll need to know fractions and division in modular arithmetic. And of course, this will require you to use the Euclidean algorithm over and over again. So as I mentioned, you're not going to have to find directly use the Euclidean algorithm, but you will have to use it as part of this modular arithmetic question. You have to do powers in modular arithmetic, which you guys have lots of experience with now. So there are, of course, a couple different methods. One is like a successive squaring, so repeatedly squaring. Another is, of course, you can sometimes use Fermat's little theorem or Euler's theorem to take a really big number and make it smaller in terms of powers. You'll need to do roots in modular arithmetic. So this is the subject, of course, of this week's quiz. So hopefully you have a lot of studying done on that. So this will require you to make use of the inverse Euclidean algorithm and equivalent powers, as well as Euler's theorem and Fermat's little theorem. The Fermat primality test. So there's a question in the chat about, is there a proof question? So I will ask you to prove that a number is either probably prime or composite using Fermat's primality test. So that is the only proof-like question I'll ask. So if I ask you to prove that a number is composite, all you need to do is you need to find a witness, right? Saying that the number doesn't pass Fermat's primality test. If I ask you to prove that it is prime with some probability, then you just need to do it multiple times, and each time it decreases the probability that's composite by 50%. And lastly, there will be a cryptography example. I will ask you to decrypt something. Hopefully, over the course of the interactive, you guys have a sense of how to do that. The one on the exam will be easier than the ones that you all gave each other. So that's the rough outline. You'll notice that there are 7 bullet points on here. That is how long your exam is. It is about the same length as the prior exams from previous years that I posted on the course website. If we have a little bit of extra time, I might actually go through one of those with y'all. So it'll depend a little bit. But first, I'm going to go through, and for each of these 7 categories, let's see a baby example of one, just to remind you all of all things you guys have learned. So, prime and composite numbers. Well, what's a prime number? A prime number is any number that's divisible by only 1 in itself. Hopefully you know it by this point in this class. If you don't, well, you have a lot of studying to do. So, for example, you have things like 2, 3, 5, etc. And you also have things like 17, 23, 97. I will give you a list of all the prime numbers smaller than the 100. But these are prime numbers. And of course, these are multiplicative building blocks. So for example, 36 is equal to 2 squared times 3 squared. 150 is equal to 2 times 3 times 5 squared, and so on. And you can find prime numbers up to n by using the sieve of Eratosthenes up to the square root of n. So for example, if I wanted to find all the prime numbers between 21 and 25, I could write out the numbers from 20 to 25, and I could be like, oh, are these divisible by 2? 2? Well, you rule those out, so none of those. Are they divisible by 3? You rule those 2 out. Are they divisible by 5? Let's get rid of those 2. And of course, now that you've gotten up to square root of 25, which is 5, you can stop. And so they aren't going to be divisible by 7. Or I mean, if they are divisible by 7, they've already been ruled out by one of the other numbers. Okay? And there are a couple different ways of finding runs of numbers. So maybe I want to find a run of 3 numbers, run of 3 composites. So one way of doing this is you could just list out all your numbers and wait until you find, so maybe you're like, oh, well, 2, 3, 7, 11. Oh, wait a moment. That means 8, 9, and 10 are 3 non-primes. So that's one way you could do it. But of course, for really long runs, that's going to be harder because then you're going to have to list out more things. So another way of doing this is to use the factorial trick, which we covered in class, which is it turns out that 4 factorial plus 2, 4 factorial plus 3, and 4 factorial plus 4 are all going to be divisible by 2, 3, and 4 respectively. It turns out this is actually going to be 26, 27, and 28, which are divisible by 2, 3, and 4. And so you'll notice that on the prior year's practice exams, or sorry, prior year's exams, they'll ask you for like runs of 5 composites or 6 composites or 7 composites or things like that. And you could list out all the numbers and try to find them, or you can use this factorial trick. Okay, any questions about primes and composites? Okay, what else did we do? We did divisors and relative primes. And so, for example, you might notice that given the factorization, it's pretty easy to use the exponent to determine the number of divisors, right? So for example, 120, well, you want the prime factorization of this. Let's split that up. Let's say 10, 12, 2, 5, 3, 4, 2, 2. And so that's equal to 2 cubed times 3 times 5. So the number of divisors is going to be equal to 3 plus 1 times 1 plus 1 times 1 plus 1, because each of these is actually for 1 power. So that's those 2 pieces, and that's that. So you multiply these together, and that gives you 4 times 2 times 2, which is equal to 16. Oh, can I turn off the lights again? Yes, yeah, sorry about that. Okay, and the other thing is, given a factorization, you can use the primes that are present to determine the number of relative primes, to compute the phi function, which is something that you all should be pretty familiar with now as well. So for example, phi of 120 is going to be equal to 120 times 1 minus 1/2 times 1 minus 1/3 times 1 minus 1/5, because the primes present are 2, 3, and 5. So there are a couple ways you can write this out. However you solve it, you're going to get the answer. One way to doing it is do each piece at a time. So this piece here is 60. So this is 60 times 1 minus 1/3 times 1 minus 1/5. This piece here is going to be 40. So 40 times 1 minus 1/5. And so that's equal to 32. But you can multiply that however you want, or just use your calculator. Okay, and that gives you the number of relative primes known as Euler's Todian function. And of course, it's easy if something's just the product of 2 primes, as we were seeing earlier, because then that's an easy case. But this is the general case. Any questions about that? Great. So now we get to modular arithmetic. So there are a number of different ways that we figured out of solving fractions in modular arithmetic. I'm going to cover only one of the ways right now, but of course we covered a couple different ways back in lecture. One way is to compute the reciprocal by finding a combination for one, and then you multiply. And this will always work, assuming that the GCDs work out properly. So 3 divided by 12 mod 17. Well, how do we do this? Well, in order to do this, you use the Euclidean algorithm, and you get, let's see, 17 is equal to 12 times 1 plus 5. 12 is equal to 5 times 2 plus 2. 5 is equal to 2 times 2 plus 1. And so then you can back solve for 1. So 1 is equal to 5 minus 2 times 2. So 1 is equal to 5 minus 12 minus 5 times 2 times 2. So 1 is equal to 5 times 5 minus 12 times 2. And then 1 is equal to 17 minus 12 times 5 minus 12 times 2. So 1 is equal to 17 times 5 minus 12 times 7. Okay? And once you have that, well, then you can take mod of 17 on both sides. And so that gets you 1 is congruent to 17 times 5 minus 12 times 7, mod 17. But of course, in mod 17, 17 is the same as 0. And so 1 is congruent to minus 12 times 7, mod 17. And divide by 12 on both sides, because we know that we can divide by 12, because it's relatively prime to 17. And you had the combination. So then 1 over 12 is congruent to minus 7, mod 17. And you can rewrite this as 1 over 12 is congruent to 10, mod 17. And so then therefore 3 over 12 is congruent to 3 times 10, mod 17, which is congruent to 30, mod 17, which is congruent to 13, mod 17. And yes, there are other ways I could have done this a little bit more quickly, but finding a reciprocal like this will generally work. And of course, you can check your answer. So you can always check your answer by asking 13 times 12, is that congruent to 3 mod 17? And so if you check that, you can figure out whether you got the right answer. So if you end up having extra time on the final exam, I'd recommend you go back and check that your answers are actually correct. Ideally using a slightly different method. Should you study this lecture slide for the exam? You should study, so the official line is always going to be, you should study everything we've covered in this class. Having said that, there will be a problem where I ask you to find a fraction in modular arithmetic. So it will be slightly, so the problems I'm doing in this review are going to be slightly shorter than the ones that are on your actual exam, for the most part, because I want to be able to do them all quickly in front of you. But there will be problems of this kind. You learned about composites in the same, composite numbers are just numbers that aren't prime. So they should have been in the lecture where we learned about prime numbers. Okay. We also now, we're moving on to modular arithmetic. So, I mean, powers in modular arithmetic. One way is you can successively square things and then rewrite as a product of the sum of powers of 2. So for example, you have a to the 18 is equal to a to the 16 times a squared, and so on. So that's one way of finding these numbers, is to and then you can compute a to the 16, because then you can get a to the 1, a to the 2, a to the 4, a to the 8, and a to the 16. Another way of doing it, if I give you a really, really big power, which you should expect, is you can use either Fermat's-Little theorem or Euler's theorem. So Fermat's-Little theorem only works with prime p, and both of these theorems only work if the greatest common divisor of a and n, or a and p, is equal to 1. So how do these work? Well, we know Fermat's-Little theorem says that 2 to the 4th is congruent to 1 mod 5. So that means that 2 to the 10 is congruent to 2 to the 2 mod 5. Okay? And similarly, 2 to the 8, so it turns out that, let me actually write this out, phi of 15 is equal to 3 times 5 times 1 minus 1/3 times 1 minus 1/5, which is equal to 8. And so 2 to the 8 is congruent to 1 mod 15. So 2 to the 17 is congruent to 2 to the 1 mod 15. Okay, so you can just add, multiply by 2 to the phi of n, or add that to your exponent. Any questions about all that? Well, let's keep on going. Now we get to some of the harder stuff. So roots in modular arithmetic, they get quite hard if your numbers are big, as we've all discovered today. I will not have your numbers be all that big. They will generally be 2-digit numbers. And so hopefully it won't be too bad. But let's give an even easier example so that we can do this just right now in class. So what is the cube root of 2 mod 15? So the cube root of 2 mod 15. Well, in order to do that, you need to first find phi of 15, which is equal to 8. And then the things you need to check, GCD of 2 and 15 is 1. And the GCD of 8 and 3 is 1. And so this means we can't actually use this method. And now what we're going to do is we're going to be like, oh, well, what's 8 is equal to 3 times 2 plus 2. 3 is equal to 2 times 1 plus 1. So therefore, 1 is equal to 3 minus 2. 1 is equal to 3 minus 8 minus 3 times 2. So 1 is equal to 3 times 3 minus 8. Which is correct. You can double check that 9 minus 8 is indeed 1. So once you have this, well, then that also means that 1 plus 8 is equal to 3 times 3, just by shifting things around. And so therefore, you know, the cube root of 2 is congruent to the cube root of 2 to the 3 times 3, which is also, of course, 1 plus 8, which is congruent to 2 cubed mod 15. So overall, this means that the cube root of 2 happens to be equal to 2 cubed mod 15, which is congruent to 8 mod 15. Any questions there? Okay, so let's go on to primality testing. So in order to do primality testing, consider a random number n, which may or may not be prime. You pick a random number a, You take a to the n minus 1, and you check to see if that's congruent to 1. If it's not congruent to 1, then a is composite, and that's all you need to say. Otherwise, n passes the Fermat primality test, which decreases the chance of it being composite by at least 50%. Let me give 2 examples. So let's give an example of n is equal to 11. So we know this is prime, but let's check to see if this is prime by doing the Fermat's primality test. So 2 to the 10 mod 11. So I'm going to do this the fast way because I happen to know that 2 to the 10 is 1024. But of course, there are several different ways you can do this. 1024 mod 11. And if you divide that out, that ends up giving you 1 mod 11. So you can check that. You can just use a calculator, or you can use long division. Similarly, 3 to the 10 mod 11 is going to be congruent to, I'm going to rewrite this as 9 to the 5 mod 11. So notice that I'm not using successive squaring. You can do it. I'm doing, but if you're clever, you can sometimes do it a slightly different way. So this is 9 to the 5 mod 11, which is congruent to minus 2 to the 5 mod 11, which is congruent to minus 32 mod 11, which is congruent to 1 mod 11. So now we've checked it for 2 different numbers. So what does that mean? So together, this means that there's a 3/4 chance that it's prime, at least. And it is prime. On the other hand, if I had another number, let's say n is equal to 9, and I took 2 to the 8 mod 9, well, that's 256 mod 9, which happens to be equal to 4 mod 9. And so this, when you do that, that implies that 9 is composite. Okay? Any questions about that? So basically, in order to use Fermat's primality test, you pick a random number. If a to the n minus 1 is not congruent to 1, then you immediately know it's composite and you don't have to do anything else. I mean, you have to say that it's composite, but you don't have to do anything else. On the other hand, if a to the n minus 1 is congruent to 1, well, you don't know for sure, but there's at least a 50% chance that it is prime. If you do it repeatedly, you increase that chance from 1/2 to 3/4 to 7/8 and so on. You're decreasing the chance by 50% that it's composite each time. Anything else? Okay, and lastly, we also have this cryptography section, which is the last week and a half or so. So the Caesar cipher is pretty easy. You're just shifting all letters by a fixed amount in the alphabet. A, B, C goes to C, D, E if you add 2. And if you subtract 2, you can decrypt it to get back to A, B, C. You all have a lot of experience with that now, shifting backwards and forwards. But just remember that you need to shift, add to shift to encrypt and subtract to decrypt. We also have RSA public key encryption, which makes use of the fact that factoring and square roots are hard. So as you've experienced, taking square roots, factoring and roots, not square roots. Factoring and roots are hard in modular arithmetic. Well, see previous interactive. And I will give you a worksheet. I'll hopefully write it by Monday with a couple more examples of this. And of course, in hybrid cryptography combines them both. So you use public key encryption to send a small key for the Caesar shift or other symmetric encryption. So this is also this interactive exercise. And that's it. So if all of that made perfect sense to you, then question. How do you feel about the final? Now that you know what's on it. Are there going to be trick questions? I will decline to answer that question, but maybe you can infer something from how long it took me to figure that out. So, let's see. So on the exam, are you encrypting or decrypting? You are decrypting. Having said that, there won't be any. I don't think I put any super ugly tricks on there. Any tricks that I might have put on, you can solve the normal way. The only difference is you might be able to solve it faster if you see a trick. So the standard way of solving these things will always work. You do need to check your conditions. So you do need to check your greatest common divisor conditions, or sometimes the things just won't work. Okay, so looks like we have a good mix. Hopefully, in another week and a half, after a little bit more studying, you all will feel a little bit more confident. With that, that is it. Oh, I think I duplicated this slide. You made it to the end of the magic numbers. I am happy to take questions now, or I can look at a previous year's final and then just go through and talk about it if you all have questions about that. No, there is not. The questions that you see, the 7 types of things that were on this review PowerPoint are the 7 types of things I will expect you to know.